So I said a while ago we were going to see more details about these electromagnetic waves and the fact that since they're waves, they carry energy and they exert pressure. So let's first think of the energy in these waves, or more particularly right now, the energy density. We're not going to go into great detail of where these came from. You would have seen where this came from already in the previous semester when exploring electric fields, magnetic fields. You eventually got to the point where you're thinking about the energy density of those fields, and it turns out that it's just related to or proportional to the square of those fields. So the energy density in an electric field is just 1/2 epsilon naught times the electric field squared, magnitude of the electric field squared. The energy density in a magnetic field is just 1/2 or 1/2 mu naught times the magnetic field squared, magnitude of the magnetic field squared. And given that we found from our wave analysis that the electric field is equal to speed of light times magnetic field, or that the ratio is equal to the speed of light, that information allows us to rewrite this energy density in terms of just the electric field or just the magnetic field. And also the fact that C, remember, is equal to 1 over the square root of mu naught, E naught, epsilon naught. Sorry. This slide is to kind of connect together what we know maybe about waves already to then what we already knew about electric and magnetic fields and their energy density. We know from analysis of electric and magnetic fields, their energy density is related to the square of those fields. But now we know that electromagnetic fields produce waves, and waves, the intensity of a wave, or essentially the energy density in a sense of the wave, is proportional to the square of its amplitude. So now those things hopefully make a little more sense together, where our electromagnetic wave has an amplitude that's defined by, well, in one direction the electric field, the other direction the magnetic field. So the intensity of these waves is just related to the square of those fields, just like it, because those are the amplitudes of those waves. So just like any other wave, the energy density or the intensity, in a way, is related to the square of these amplitudes, electric and magnetic field. So then if we want to consider what the rate of energy, or the rate that energy is transported by these waves, then, well, we could think about this sort of surface where that energy is going to be deposited, and then imagine this sort of tiny cylinder over a very short amount of time, how much energy is in that little cylinder that's going to be deposited on that surface. Well, we know the energy density of those waves, then the amount of energy in that little cylinder is just the energy density multiplied by the volume of that cylinder. U multiplied by the volume, and the volume in this case, if the circular surface of this cylinder is area A, then the length of this cylinder is going to be that delta t, that tiny amount of time, multiplied by c, the speed of that wave. That's the length of it then. So the volume just looks like U, A, C, delta t. So this then would be the energy transported in the sort of in this cylinder in this tiny little amount of time. But what about the energy, say, per area per unit of time? That then gets us to what we call the Poynting vector. So if you take that energy that we had before that's transported in that tiny amount of time, then you say, okay, what about the energy per area per unit time? Then we just divide by the area of that surface that the energy is being deposited on and the amount of time that we're thinking about. And all that ends up, well, from the past relationship, A and delta t go out of that equation, and we're just left with energy density multiplied by the speed of light. And then looking back, how the energy density is related to electric and magnetic fields, we can write this S as equal to, well, epsilon naught c times the magnitude of the electric field squared, or we could write it as 1 over mu naught, electric field and magnetic field, magnitudes multiplied. In general, though, this thing that we're talking about is actually a vector quantity. That's what we call the Poynting vector. And you can get it by the cross product of the electric and magnetic field vectors, just like this. So since it's from a cross product, the Poynting vector is perpendicular to both the electric and the magnetic fields. The Poynting vector happens then to be also always in the direction of the propagation of the field, which can be useful. And also, pointing, I think when I first heard this, I never saw it written out and thought it literally meant pointing. which it in a way does. It points to the direction the magnetic field goes. It's actually named after somebody, I think, whose name was pointing with a Y. So confusing, but I guess if you didn't get that it was a name, it still kind of makes sense. But a random tangent, I just heard recently that apparently gray whales are thought that maybe they're not actually named because of their color, they're named because of a guy named Gray who named them, or who spotted them or something. So it's another example of, I thought that name was meaning one thing, and it doesn't actually mean that thing, but it still makes sense. Weird. You might notice different clothes. Couldn't quite finish filming this chapter all in one chunk, so I had to wrap yesterday back today. There you go. You get a second t-shirt for the same chapter, all of you are. Right, so we were talking about pointing vector, and it's a very useful thing, but typically the things that you're going to measure on a macroscopic scale are sort of average out a little bit, right? This is kind of a microscopic quantity, and it's more useful to think of things that you might actually measure, like the intensity of the light, which is sort of like averaging this energy deposit over a cycle or many cycles, cycles being the oscillations of the electromagnetic wave. We might use a quantity like the intensity, which we would just quantify as the average of this pointing vector. In the book, they actually show how you do this average, but essentially you're integrating something over a period and then dividing by the length of that period. It turns out you're essentially integrating a cosine squared function over a full period, and they show in the book, and this is a kind of a common thing that might come up, when you integrate cosine squared or sine squared over a full period, you end up getting a half. So this is why the intensity ends up being basically a half. Yeah, how does that factor of 1/2? And the top here is just with the electric field. Then that E0 is the amplitude of the electric field, right? E0 times the cosine, that stuff. So the intensity has to do with the square of the amplitude of the electric field. And given that the electric field and magnetic field are related by the speed of light, we can also rewrite the intensity, or the average of the pointing vector, in the average of the magnitude of the pointing vector, I should say, in these other ways, with the magnetic field amplitude, or if you want the electric field amplitude and the magnetic field amplitude. All right, so time for an example. I don't know if I did an example yet in this chapter, but there's kind of a lot here, so saving up for some. So in this example, we're thinking about a light bulb, and that light bulb is giving off light, electromagnetic waves. Overall, we generally know the power of a light bulb. It's usually given in watts, energy per time. Here is 5 watts. And we're asked, what is the average electric and magnetic fields from this light at a distance of 3 meters? So the intensity of this light is going to go down as we move away from the source, because that power that's being emitted by the source is spreading out over this area, over this spherical area to be exact, as it moves away from the source. So essentially what we're going to need to do is take that power and then divide it by that area that it's now being spread over, which is a sphere, the surface of a sphere at radius r. So the power, say 5 watts, the radius we're asking us about is 3 meters, 10 feet or so. So again, if it spreads over that spherical surface, then we can find the intensity by just seeing how that power is spread over that surface. But then from the previous slide, or the slide before that, we know that the intensity is related to the electric field amplitude or magnetic field amplitude. So this intensity is also equal to C epsilon naught squared over 2. So that means we can relate these two things, and we know this power and this radius, which will allow us to find the amplitude of the electric field at that distance from the light. If we were to solve for that, it would look just like, so 4 here. Get that. If we were to put all these values in, I'm not going to write all the units, all these units are SI units or standard units, so we should expect to get newtons per coulomb out for the electric field. And this is that electric permittivity of free space. There's a lot of units associated with it, but overall, we end up getting 5.77, and that is again going to be newtons per coulomb. There's other ways of writing the electric field, the units of the electric field, but that's one of the more standard ways. So that's the electric field amplitude. What about the magnetic field? Well, we could go through a similar process starting from the intensity, or we know that the electric field is related to the magnetic field in this way, or the ratio of them is equal to C. So if we just divide the electric field we got by C, the speed of light, again, everything's standard units, so you can just assume we're going to get out the right standard units, which is Tesla's. 1.9 times 10 to the minus 8. Right? And this is again showing that the electric and magnetic fields, their magnitude, like how large they are overall, the electric field is much, much larger than the magnetic field. So, and we're going to see in just a minute that when we go to look at, or kind of try to understand some of the things that happen because of the fact that there are these electromagnetic waves, well, some of these cases we'll just kind of look at the electric field and what it does when it interacts with, say, electrons, because it's so much larger than the magnetic field that it's doing most of the stuff that's happening has to do with the electric field. Right. So I said in the very beginning, we're going to see the momentum and pressure that these electromagnetic waves will exert because they are waves. And in thinking about the momentum that's transferred, I guess momentum being transferred, pressure might be exerted, but if you think about the momentum that's transferred by these waves, it will depend on whether or not these waves are being absorbed by whatever it is they're landing on, impinging on, versus if they're being reflected. So if the electromagnetic wave is fully absorbed, well, the thing that the absorber is doing is just taking all that energy in. If it's being reflected, however, then it's taking all this energy in, and then it's actually rebounding that energy too. So in a sense, there's a doubling process that's happening where the radiation pressure that you would expect for a reflector is actually twice what you would expect for the absorber. Because the absorber is just taking it in, but the reflector is actually having to re-put that back out. So we can just relate the radiation pressure to the energy density of these waves, just like shown here. The book goes through some unit analysis just to make it clear that energy density does in fact have units of pressure. And then remembering that energy density was related to the Poynting vector, the magnitude of the Poynting vector, and that Poynting vector we related to the intensity overall of the waves, gets us to thinking about the average, right? Because the intensity was related to the average of the Poynting vector magnitude. So the average of that radiation pressure we can relate to the intensity of these waves very straightforwardly, very simply. Intensity over speed of light, or twice the intensity over speed of light, depending on you're talking about the absorber or the reflector. So this is an example of say an apparatus that we might use to measure the pressure, that radiation pressure, or the pressure due to electromagnetic waves hitting a surface, where pretty simple, you just have these two mirrors and they're tied on to some kind of string fiber and allowed so that they can sort of rotate around freely, right? Balanced out so they're not doing all this, but that they can nicely rotate this way. Since they're able to rotate freely, it takes very little pressure to actually get that movement, cause some movement, and it turns out that this sort of setup allows you to measure very small pressures being exerted, or very small forces over the surface of the mirror, right? Which is nice because it turns out these radiation pressures are extremely small. This sort of torsion apparatus is generally a nice way to measure very, very small forces. So I believe that one of the early measurements that was made of Newton's gravitational constant was also using this torsion setup where you have these two masses that are on these, or at least one is on this torsion setup, and so you can measure this very, very tiny gravitational pull between the two masses, just because it's torsioning that fiber just a little bit. So this is actually from another example that the book shows. We're not going to go over it, but it's a pretty straightforward process. Sort of putting quantitative values down to what I was saying at the very beginning of this chapter, that the sunlight is actually exerting pressure on the tail of these comets. It still is very small, like I was saying a minute ago, but it's there. In the last part of that example, they actually show you that the gravitational force on, say, like a chunk of this comet that fell off, the gravitational force from the sun on that chunk is still like 100,000 times stronger than the radiation pressure. The radiation pressure is 100,000 times less than the gravitational force. So this radiation pressure is, like I said, is very tiny, but it's there. And the fact that it is there is a nice confirmation of Maxwell's predictions. All right, so we didn't actually look at the last example in detail, but let's look at this one about what's known as a light sail. I guess that might be a proprietary term. Solar sail, I think, is actually the more general term. But this fact that there is radiation pressure from sunlight, people thought, well, could I use that to actually propel, say, some kind of spaceship or spacecraft and not have to use other kinds of fuel? And yes, I mean, you can. Might not be very efficient, but you know, you're getting that push, that pressure basically for free, so if you can use it, then maybe figure out a good way to use it. Sort of the idea is that you have your craft, but it has a very large and very lightweight reflective sail, in a way. And when you deploy that sail out, then all of the radiation pressure that's hitting that sail is going to help propel the craft. And since it's a reflector, you get the most out of it, right? You get the double the pressure. Okay, the intensity of energy from sunlight at a distance of 1 AU, the average distance from the sun to the earth, is 1,370 watts per square meter. The light sailcraft has sails with a total area of 32 square meters and has a total mass of 5 kilograms. Calculate the maximum acceleration the spacecraft would achieve from a radiation pressure when it's about 1 astronomical unit from the sun. Okay, well, if we want to know how much it's going to accelerate, we're going to figure out the force that's being applied first from that pressure. So the force, pressure is equal to force over area, so force that we're going to get is the pressure multiplied by the area. And since these are reflectors, that pressure is going to be twice the energy density of the waves that are hitting, which finally is going to be twice the intensity of the light divided by the speed of light multiplied by that area still. Put all these values in. And then we're going to get, what is that? 2.92 times 10 to the minus 4th newtons. So, fairly small, but you might expect that because we're dividing by the speed of light. What about then the acceleration that this 5 kilogram spacecraft would experience? Well, it's that force over that mass. So it turns out you just divide that by 5, and you get 5.8 times 10 to the minus 5 meters per second squared. Again, pretty small force. The mass is, you know, not tiny, it's substantial, so the acceleration is fairly small too. I think the book actually goes through to say that if you had that acceleration for a year, though, you could get up to a speed of like 1,800 meters per second, which is about 4,000 miles an hour. So it's possible to be a useful sort of thing. The fact that they just assume the same pressure exerted over that whole year is a little bit wonky. Like it's going to change because if it's getting pushed away from the sun, it's going to be further from the sun. The intensity is going to be less. You get less pressure, but still, you get a somewhat of an idea that even though this pressure is very low, if you have a large sail, you have a fairly light craft, you can actually get it up to pretty large speeds over a maybe reasonable amount of time. I don't know if that's reasonable. And then the last thing to keep in mind then too is that since it's traveling through space, any acceleration that gets put on that sail, it's just increasing its velocity, and there's no friction, there's nothing to slow it down. So it's always, all those gains are just continually added on, which is very nice in the situation. So now we have much better sense of the wave nature, or particularly like the mathematical description of the wave nature of electromagnetic waves. So that includes light that we looked at quite a bit, but it also includes all these other things: ultraviolet light, infrared light, X-rays, microwaves, gamma rays, radio waves. So they're all electromagnetic waves, it's just that their wavelength is different. For the visible light, it's somewhere in the range of like 400 nanometers to 700 nanometers, roughly around there. We work with that quite a lot, but if you get much smaller than that, then you start to get into ultraviolet light, X-rays, and gamma rays. You get much larger than that, you get infrared and then microwave and radio waves. You can also characterize these waves by their frequency, right? Because you assume they're traveling at the speed of light, then the speed of the wave is related to its wavelength and its frequency. So the bottom on this bottom chart is showing frequency. Oh, I guess it's also shown here. But one of the interesting displays here, I think, is also that it's showing a relative size of these waves. So when we're talking about radio waves, it could be up to almost any length, but something like the size of a building maybe, right? All the way down to around the size of like a person. So tens of meters down to, or 1,000 meters maybe, down to like a meter or two. Talk about microwaves, right? They have an example of like a little bee. Infrared waves, we're getting down to the size of like the head of a pin. Visible light, size of protozoans, or like, I don't know if that's single-celled or multi-celled. Very small though. We're getting quite small. And then ultraviolet waves down to molecular scale, X-rays down to atomic scale, then gamma rays finally down to that nuclear scale, atomic nuclei. So these are just different ways of looking at the electromagnetic spectrum. And then maybe a little bit more closer look at the radio and microwave portions of that spectrum. They're highly utilized in our modern day for transmitting information, anything from AM radio, FM radio, to cellular networks, Wi-Fi, satellite communications. All that stuff is pretty integral to our modern day life. So it's interesting to note, I guess, kind of this is the area where that's taking place and how useful it is overall. Something that came to mind when I was looking through this, there are some concerns, or at least in particular places, about the harmful effects of, say, cellular towers that are transmitting waves, around the same wavelength that microwave ovens use. Right? And microwave ovens cook food, so it seems like maybe there's an issue there. If you look at it though, the microwave ovens are typically, I think on average, I found they're typically like 700 watts, right? That the amount of power that is being utilized there, and the distance from the source to the object, like the food that you're cooking, is maybe like 10 centimeters or something. So the intensity of the waves from that microwave onto the source is very high. You get a very high intensity there. Whereas the cellular towers are sort of, I think by law, limited to like 100 watts or maybe 200 watts. But it's several times less than the average microwave. And then on top of that, the closest you're going to get to the source of these things is probably like 20-ish meters, I don't know, 10 to 20 meters at least. And that's about as close as you're going to get. And even at that range, it turns out you could do the math and look at the intensity, like we just did with the light bulb earlier. Turns out that intensity is like several 100,000 times less than the intensity of the waves that are on a microwave oven. So sort of like comparing little ripples in a pond to like a tsunami. But speaking about microwave ovens, just to note real quick what is going on there when you do have that very high intensity impinging on these molecules is generally affecting the water molecules in the food or when you're heating up. If you think about the electromagnetic waves that are passing by, right there, the electric field is going up and down, up and up, up and down, up and down, and the fact that the microwaves are something like, forget, in the gigahertz range, which means they're reversing their direction like billions of times a second. Essentially, the electromagnetic field is going up and down billions of times a second, and it's acting as like a torsion on these water molecules, right? Because water molecules are polar. There's a sort of positive side and a negative side, so it wants to align itself with that electric field. Since the electric field shifts, it constantly goes back and forth, which is essentially just dumping thermal energy into the water molecules and then fizzles out into the rest of the food. This is just an interesting table from the book, sort of related to the very top of the electromagnetic chart that I was talking about earlier, with like the sizes of things related to the wavelengths. The production associated with each of these things is pretty interesting. So like microwaves are generally, like I was saying a second ago, they're associated with charges that are accelerating or thermal agitation, like jiggling of atoms and molecules or rotating of atoms and molecules, versus say like X-rays, which are going to be associated with electron transitions in atoms, so electrons moving from different higher energy levels to lower energy levels, emitting X-rays, and all the way to gamma rays, right, which are associated, or on the size of the nucleus of an atom, and they're associated with nuclear decay generally, or nuclear processes more generally. Right, so that's actually where I want to kind of end with the electromagnetic wave chapter, and as I decided and told you a while ago, I thought that the polarization information from chapter 1 of the volume we're generally working in volume 3, that made a little bit more sense to look at later on after we had a little bit of understanding of electromagnetic waves. Still think that's probably a good idea. I don't know. Hopefully it doesn't make this lecture overall too long. But we're going to talk about polarization now. So at a very basic level, polarization is sort of a direction associated with an electromagnetic wave. Very simply, the direction of the polarization of an electromagnetic wave is along the axis of the electric field of that wave. So like this picture here, that arrow maybe should be just tilted a little bit, but it's trying to indicate that the direction of polarization is sort of vertical here. And since it's along the direction of the electric field, it's always going to also be perpendicular to the direction of motion of that wave. So then there's something called a polarizer, which is sort of a filter for electromagnetic waves, and it filters them by their polarization. And we can use an analogy where, like the wave, instead of an electromagnetic wave, think about the wave created when you oscillate, say, a rope, and then the polarizer is basically just a slit. So in this first picture, we have a rope, we're oscillating that rope up and down, that's the direction of the polarization, up and down with the rope there, like the direction of the electric field, say. So up and down is the direction of the polarization, and if the polarizer, right, which we're imagining as this just screen with a slit, if that's also laid up vertically, then these waves are able to transfer through that, right? I can go up and down, the rope can go up and down in the slit, and it just keeps going. There's no stopping it there. But if instead the direction of the polarization of the wave is horizontal, right, if I'm going left and right with this rope, when it tries to go through that vertical polarizer, right, this vertical slit, right, it's just going to keep running into the sides of that slit, and so the wave's not going to be able to pass through. So this is a conceptual way of understanding, like through analogy, how a polarizer works. So a vertical polarizer will allow vertically polarized light to pass through. It will block horizontally polarized light. And then if you just rotate the polarizer 90 degrees, now it's a horizontal polarizing filter, so it will allow horizontally polarized light, but block vertically polarized light. Now we're going to think what's going on kind of an atomic scale. Again, not too deeply into the details of it, but at least give you an idea. And that is that these polarizers are generally made up of these sort of long chain molecules, right, as shown in here. All those dots are little atoms, and together they make up these long molecules, sort of linear molecules. And as I mentioned before, when we've done, we're mostly just going to think about the electric field, because that's much larger than the magnetic field. And beyond that, when we're talking about its interaction with these molecules, the thing that it's going to mostly be able to interact with and cause the most effect on are the electrons in these molecules. And that's just because the electrons are so much lighter than the protons and the neutrons in the nucleus of the atoms that make up the molecule. So if we do just think about the electric field wiggling along and how it interacts with the electrons in these long molecules, then we can get an idea of how these polarizers are working on a molecular scale or atomic scale. We think about, say, on the left here in A, the electric field, say, is horizontally polarized, or that light is horizontally polarized. Remember, because the electric field direction is the direction that we define the polarization. So if you have this electric field and this light that's horizontally polarized, it's coming along and it's going to impinge and try to pass through this sort of wall of these horizontal molecules laid out. What's going to end up happening is that the electrons, right, they're part of these long molecules, but since the molecules are laid out horizontally, the electrons can actually move a good bit along the molecule. Right? So they have some freedom of movement to move along this chain. So when the electric field comes through, it's actually able to move those electrons a good bit horizontally, but that movement requires energy. So the electric field is kind of giving energy to these electrons in order to move them along the molecule, which means that the electric field that ends up passing through has lost energy. It's going to be smaller, or its amplitude is going to be smaller. So this is one way of understanding why, if you have this polarizer with these long horizontal molecules, it's actually going to block a lot of the horizontally polarized light. Versus the vertically polarized light that comes through, right? The electric field is vertical. The electrons now are going to be trying to move up and down, right? But they don't really have a lot of freedom of movement to move up and down because they're in these long horizontal molecules. So since the electric field can't actually even move them very much, there's not a lot of energy being given to those electrons. So the electric field that comes through ends up being fairly similar to the one that came in to begin with. Meaning that vertically polarized light is actually going to pass through these horizontal molecules, these long horizontal sort of stacked molecules. It turns out that most often when light is created, or the light that we get from, say, like the sun, these fluorescent bulbs, light bulbs, flames, right, that light is just randomly polarized. It doesn't come out all with the electric field wiggling in one direction. It can be a little bit odd. The stuff that's creating it is just very random. So the polarization directions of those waves that are being emitted is also pretty random. We can use polarizers to filter out all of those other directions. So say if we have this vertical polarizer, the axis showing here is the axis along the direction that is polarized. And then if we have that randomly polarized light coming through, all those rays are representing the polarization direction of like many different waves that are in that space and kind of coming towards this way. Then the polarizer is going to filter out everything except for the stuff that's vertically polarized. But on top of that, the stuff that's partly vertical and partly horizontal, we're going to see in a minute that the polarizer will essentially take away whatever horizontal component there is. So some of that light still comes through, but we only get the vertical component of that, or the component that is in the direction of this polarizing filter's axis. Yeah, so you can think about randomly polarized light, say just pick one of those off-axis arrows, right? We could write it as a combination of how much polarization is in the vertical direction and how much polarization is in the horizontal direction. So in a very real sense, the horizontal and the vertical are sort of these bases for the space of polarization. Sort of like I hat and j hat are the basis for the xy plane. If you didn't understand that basis stuff, that's okay. Just threw it in there because I think some of you are probably, or I know some of you are in linear algebra, and so hopefully getting a little bit of understanding of basis vectors and spaces. Okay, so if we have polarizers, right, they're going to allow the light to come through that's only along the axis of that polarization, or the component of the light that was only in that direction. It's an interesting thing to think of is what if you have two of these polarizers, right, and you kind of adjust the rotation relative to the first one. Right? So you have the first polarizer, you take a second one, and at first if you align it with the second one, so both of their axes are vertical, like in picture A, then whatever light comes through the first polarizer is all vertically polarized, and so the second polarizer is not going to stop any of that, right? All that light is already on this, along this axis, all that's going to come through. So whatever made it through the first is going to keep going through the second. But in B, say you take that first one and you rotate the second polarizer off axis a little bit. So now whatever light came through is vertically polarized, but this filter is no longer aligned vertically. So what it's going to do is only allow the component of this vertically polarized light that is along the axis of this polarizer now, right? Or you can imagine it as the polarizer just takes a projection of this vertical polarized light in the direction of the polarizing axis. And so we get a smaller amount coming out. And then finally, if you take the polarizer vertical and then you twist the other one 90 degrees, they're now 90 degrees from each other, meaning that all the light comes through is vertically polarized here, right? But we now have essentially a horizontal polarizer, and since this light is all vertically polarized, there's no component that's horizontal, so it's going to block all of that light, and you don't get anything out. So all that also is to say that the angle between these two polarizers, right? One of them, say, is vertical, the other one you turn to the side, so there's this angular difference, right here between those two axes. That angle is affecting how much light is going to end up going through both of them. When it's 0, however much light comes through the first, you're going to go through the second. When it's 90 degrees, there's going to be nothing coming through because vertical meets horizontal. And in between, you're going to get some amount. Well, in between all of it, none. And that comes down to something, it's called Mollis's law. If the polarizer is off axis, then essentially it's going to take a projection of whatever light is coming through, whatever polarization of that light is coming through, is going to project it onto the axis. And you get just that component that is in the direction of the filter's axis. So if you look at that projection, it has to do with the cosine of that angle in between the light coming in and the axis of the polarizer. So the electric field gets cut down by that factor of cosine theta. The intensity, remember, is proportional to the square of the electric field. So the intensity of the light that comes through a polarizing filter turns out to be that related to the cosine squared. So besides using a polarizing filter, there are other ways that light becomes polarized. One is through reflection. We're not going to go into great detail into these other things, but the way I would think about it actually is that if you have light, say, that's coming into this surface, say like the surface of a pond, and it's kind of randomly polarized, or sometimes called unpolarized light, coming in, then you can sort of think about that light, or the polarization of that light, think about it as maybe like a skipping stone, right? You have like a stone that's pretty flat, round, and if you throw that stone horizontally, right, so that the flat side is sort of along the, or parallel to the surface of the water, then that horizontally positioned stone is much more likely to skip along the surface of the water, right? It doesn't actually go in, it reflects. Versus if you take that same stone, but you have it vertical, and you throw it to the water, right, then it's much more likely to just pierce through the water and go through. And so that light, when it's vertically polarized, is much more likely just to go through and refract. So this is one way of understanding or thinking about why when light reflects off of the surface, or when it hits a surface, whatever light is vertically polarized in that unpolarized light, or that component of it, is more likely to refract and go through, versus the horizontal component is more likely to reflect and bounce off. But it's not all of it. Like, some of the vertically polarized stuff is still going to bounce and keep going. Some of the horizontally polarized stuff is going to refract and go through. So it's not a perfect thing, but in the end, if you're looking at light that's reflected off of this smooth surface, then overall its intensity will have gone down, partly because it's now partly polarized horizontally. Yeah, so it also has to do with something called Brewster's angle. We're not going to worry too much about that. There's kind of interesting stuff, so feel free to read more into that if you like. Yeah, so this is a good illustration of light being polarized after reflecting off the surface, and then also what a polarized filter then could do to reduce that glare off the surface. So on the left, you see the clouds, a bit of an image of the clouds, and that's the light that's reflected off the surface. That's now, reflected off the surface, now coming to your eye. But again, most of that light is horizontally polarized. So if you are wearing sunglasses that are polarized, and particularly polarized vertically, then it's going to cut down all that light, or whatever component is horizontal, which is most of it. So looking through that vertically polarized sunglasses, now you don't see that glare, you don't get that reflection. So the last way that we're going to think about the way that light might be polarized is by scattering off of atoms and molecules. So in order to understand this, you have to dive into a little bit the fact that when light is traveling through a medium, it's not vacuum, it's not free space. It generally actually is being absorbed and re-emitted like continuously as it travels along. So this is partly why the index of refraction is what it is, right? With the makeup of a material slows down the movement of light because the light is actually being absorbed and re-emitted through this material. Depending on its physical characteristics, it's going to go faster or slower. Right, so if we think about that, some unpolarized light or some light with random polarization coming in and hitting this molecule, that molecule is absorbing those different polarizations, which is ends up jiggling it, sort of like we're thinking of the electric field jiggling the electron, and it's going to then re-emit that light from that jiggling that happens, and that unpolarized light is kind of moving it in all directions, right? It's moving this molecule in all directions. But if you're looking from a 90-degree angle from where that light came in, any of the movement of that molecule that's vertical is not actually going to create new electromagnetic waves along that axis direction. And you can think about that in a number of ways. You can think back to when we were looking at that dipole antenna. The movement was vertical, but all the waves were created off to the side. Along the lines of that movement, you don't actually get any electromagnetic fields. What that means here is that only the movement of the molecule that's going horizontally is actually going to produce electromagnetic waves perpendicular to the original direction that the light came in. So this is why when you have scattering of light off of molecules, then it can end up becoming partially polarized at an angle and then totally polarized at this 90-degree angle. Okay, and then the last thing to mention, just an interesting application of polarization, is for LCD screens or liquid crystal displays, which we have all over the place these days. They're extremely useful devices, things, but they rely on polarization, and they actually rely, even beyond that, they rely on a material that you can adjust its polarization based on a voltage that you apply to that material. So at a very simple level of thinking about LCD screens, you have, say, the back behind the screen itself, like there's all this light that's being created, and it's all this randomly polarized light. Look at the far left there, and that light initially passes through a polarizer, say vertical polarizer, so all the light is now vertically polarized, and there's that material in between where you can adjust its polarization. Turns out it's even a little bit more complicated than that. It's not just adjusting the polarization, you're able to rotate the polarization of the light that came in. So light will, say, come in vertically polarized, and depending on the voltage you apply to this material, it'll either allow it to just keep passing through, or it will rotate the polarization as it goes through that material. So in the one case, when you say don't apply a voltage to this material, it's set up so that it will rotate the polarization, and the next polarizer is horizontal, and so that light now it comes through. Versus if you do apply that voltage, it adjusts the material in such a way, the material adjusts itself in such a way that now that light doesn't get rotated as it goes through, it continues to go, it's vertically polarized, it hits that horizontal polarizer, and it doesn't get through, you have a dark spot. So there's a very simple way of thinking about how you turn on and off pixels in a way, right? So you have an on, right, or off due to the nature of these molecular polarizers. They're able not only to deal with polarization, but to actually rotate the polarization of these waves. If you imagine then that not just having one pixel, but instead each pixel is actually made up of, say, 3 red, green, and blue sub-pixel in a way, right? You just put red, green, and blue filters over this white light, then you can make up, any kind of color you want to. So a very basic way of understanding how LCD screens work, which you can't really not deal with them in today's day and age. And that's going to do it for chapter 16/polarization from chapter 1. And I think next time we're going to get on to actual modern physics in relativity. It should be fun stuff. All right, well, have a good one. I'll see you next time.